afternoon, everyone. This is part of my third year PhD research, and the topic is to propose an algorithm for fine-scale digital surface model reconstruction in aquatic scenarios. And this themes was born out of specific need because in my PhD I'm working with optical sensors mounted on drone that need some high resolution digital surface model to be auto-projected and used. So this is the topic of this presentation. So let's Let's imagine we have to reconstruct a three-dimensional model in a typical coastal environment. As you can see, so we want to reconstruct the three-dimensional surfaces, including trees, buildings, and everything is on bare earth. And this is a typical aquatic environment. You can find here, we are in Lake Posiano, one of my study areas, and as you can see, we have a lot of features, surface types with different structures, geometries, and textures. But also the most important thing is that we have several and different surfaces which are at the same level of water, but also above water level. For example, we can have aquatic vegetation of floating type with different species, as well as open water that are at the same elevation of water. We can also have some emergent aquatic vegetation, such as, for example, the comori that can reach up to 3-4 meters elevation above the water level, but we can also have some other flat surfaces such as meadows, rows, paved surfaces, and as well as volumetric surfaces such as terrestrial vegetation and buildings. But the most important things in aquatic environment and the most challenging things is the riparian zone. So the place in which water and the nearby vegetation meets, because it's a very complex and dynamic environment. So this is that's why we need a very high spatial resolution digital surface model that, and unfortunately some available national scale digital surface model are too far coarse for this type of environment because it's very dynamic and complex. But if we are thinking about what are the possibilities, possible sensors that we have to use for digital surface model reconstruction at very fine scale, we have several options available. The first one is the traditional photogrammetry techniques, usually are passive sensors, so they rely on reflectance measures that hit the surfaces and come back to the sensors that comes directly from the sunlight. And the data collection is two-dimensional imagery that overlap over survey areas, and in order to obtain the three-dimensional model of our surfaces, you need to processing the data, and you obtain in specific softwares, and the results is a 3D point cloud with information of three-dimensional information of points of the cloud, as well as elevation information and RGB information. But the problem is that these typical tools need some uniformly distributed ground control points. So you have to go in your survey data with the GNSS antenna to measure the exact location of some points on the ground, and in logistically difficult environments such as, for example, the wetlands and coastal environment, this could be very difficult. The second options we have is the LiDAR, light detection and ranging sensor, which is defined and classified as a active sensor. So it does not need the sunlight, the direct sunlight, but it emits some laser pulses that hit the surfaces, and that will measure the exact distance time that the laser come back to the sensors, and it measures directly the elevation as well as the three-dimensional coordinates of each point and the intensity of reflection that give us some information about the type of textures and surface we are that the sensor is viewing on the ground. And this type of technologies does not need some additional data such as the ground control points. As a result, when we reconstruct the digital surface model, here you can see that for that scene in Lake Pusiano, we have the digital surface model obtained with traditional photogrammetry on the left and the one obtained with the LiDAR sensor on the right. As you can see here, what happens that the traditional photogrammetry usually performs worst when we have some volumetric shapes, such for example trees or buildings due to some occlusions problem, for example, while the LiDAR is very mostly effective than traditional photogrammetry. But the most important things in aquatic environment is the digital surface model results over water. As you can see there, with traditional photogrammetry, we have an elevation gradient. So the interpolated water surface has some bias in elevation. It seems that something is wrong in the digital surface model obtained with traditional photogrammetry, while the LiDAR data results in a consistent water surface. And this is why this type of technology is the one that is used for trying to obtain the fine-scale digital surface model in aquatic environment. But despite the potential of LiDAR in reconstructed digital surface model over water, we have some problems, some limitations, because most of the LiDAR sensor operates in the near-infrared portion of the electromagnetic spectrum, is that one more or less between 900 to 1000 nanometers. And in this specific portion of the spectrum, we have that open water reflects very low and absorbs all the incident radiation. So what we have is that at the end we have some data gaps in our digital surface model because we don't have laser return back to the sensor, except for the natural view, because when we have water seen naturally under the sensor, we have some returns that come back to the sensor, while when we have off nadir, we have some dropouts, so we don't have water. And this problem of data gaps over water obtained with in digital surface model obtained with LiDAR data could be fixed with several tools. For example, this is a simple linear interpolation techniques that is embedded in an open source software that is called Cloud Compare, which is an open source software that manage 3D points, clouds, and as you can see there in the same study areas, what we obtained is that in the coastal zone where we have water and nearby vegetation, we have some elevation biases there, because the simple linear interpolation tends to use the elevation information provided over the vegetation to fill the gaps over water. And as you can see on the top, we can see also some inconsistency in water elevation. And this is the reason why I decided to try to propose AQUA-LIDAR, which is a semi-automatic workflow in order to reconstruct digital surface model in aquatic scenarios using only LiDAR data without the use of additional optical data, for example. And this is more or less the structure of the method. It seems difficult, but it's not. The main idea is that if we are able, starting from the raw 3D point cloud collected by our LiDAR sensor, to classify the pixels of water that are seen naturally by the sensors, we are also able to extract the water level, mean water level information provided by this data, and then use this information to fill the gaps in the digital surface model of neighboring pixels of water pixels that are seen by the sensors. Then I will explain step by step this methodological workflow. But basically, the main assumption is that water could be considered planar surface locally, and the main idea of the sensor is to trying to develop a single data source using only LiDAR data, open source, that would be also fast and simple and transferable to other sites. And the main output, the water field digital surface model, needs to be accurate and reliable in aquatic environments, especially in the transitional zones, and have to be complete over water. These to implement and to test the methods, we perform several field works. So we, with the DJI Zenius L1 sensor, which is a LiDAR sensor, but with an embedded module of the RGB sensor. So we are able to collect both LiDAR information and RGB information in order to obtain the DSM digital surface model, both with LiDAR data and traditional photogrammetry. And here you can see 6 study areas in which we perform some flights with different conditions and also challenges conditions, because we have, for example, floating vegetation, submerged vegetation. Some of them have some terrain depressions, such as Lake Massachusetts or detached points. Basically, most of them are natural environment, but we also have some man-made environments, such as, for example, Lake Garda in Site 2, the site in which we have boats, docks, and piers. Everything could be challenging in the three-dimensional digital surface model reconstruction. And starting from then, the first step is starting from the 3D point cloud. We have to find some two-dimensional features in order to that are optimal for water detections. And LiDAR, the LiDAR data allows us to obtain different information. The first one based on the height, so for example, elevation of targets within our scenes, or the standard deviation of elevation. For example, if you are thinking about water surfaces, which is the flat surfaces, basically the standard deviation of elevation of a water pixel is very low. On the contrary, volumetric surfaces such as trees or buildings has standard deviation of elevation that could be high on the corner. And then we can also derive some features based on intensity, such as intensity, which is a direct measure of LiDAR data, and standard deviation of intensity, but also another index, that is the Slayer index, which is defined as the ratio between standard deviation of the intensity and standard deviation of elevation, which record higher values on water and lower values on land, for example, and also some geometric features based on eigenvalues. So if you are looking for the local surrounding, spherical surrounding of each point of the cloud, we are able to find the eigenvalues, so the local distribution of points along the principal axis. And here we can derive the eigenvalues, and we can also evaluate some indexes that are based on the combination of these eigenvalues. And this is an example, for example, of the smallest eigenvalue, which is the one which measure along the vertical axis. And as you can see there, flat surfaces such as open water and floating aquatic vegetation or meadows, for example, has a very small eigenvalues, while they record a very high planarity, very close to 1. So the idea is to find some optimal features among these one we proposed that allows us to detect water surfaces and distinguish them from other surface data within our study sites. And based on some statistical analysis and contribution to principal component analysis, as well as with the Jeffrey-Matsushita's distance, which is a distance very used in remote sensing application that measures the separability between classes, that is ranges between 0 and 2, where 2 means a very high separability among classes, and additional random forest variable importance scores. We obtained that among the 11 tested features, these are the most effective for water detection. And here you can see an important thing, that in complex environment where we have a lot of surfaces with different types and textures, the concept of combining different types of features could be very effective in mapping water surfaces and pixels. Also, with the screening, we selected 4 of the 6 best performing features, which are height, verticality, standard deviation of the intensity as layer, and we are in the second step because this feature was going in input to unsupervised machine learning classifiers. We decided to use the Gaussian mixture model, which is an unsupervised probabilistic approach that assumes that data are defined as some imposition of Gaussian components or clusters that have unknown parameters in terms of mean and standard deviation. And within the RStudio, we used the cluster R package, which required in input the number of Gaussian components, so the number of clusters we want to classify and clusterize our scenes. So after evaluating 2, 5, and 10 clusters, we decided to use 10 clusters in order to cluster in the scenes, and with an expert-based water level identification based on photo interpretation of very high resolution RGB imagery, we are able from 10 clusters to arrive to binary scene clustering of water and non-water level, in which in this case for water level we have the direct information of the mean water level elevation. We can extract this information because that points are seen by the sensors under a natural view, so we have the information of elevation, while when we are off nadir, so in the red part of the raster there, we don't have the elevation information, but we are looking for water pixels as well. So starting from the binary scene clustering, the idea is to interpolate the scene in order to find the binary scene clustering, but with interpolating water surface. And to do so, we decided to use the R-field stats function that starting from a gap, which is the red square. We are looking for the neighbors, and we evaluated the most frequent class around the gap, and we substituted the gap with the most frequent values. In this case, we use the R-field stats function that requires 2 very important parameters that are the statistical mode for interpolation. In this case, we use the simple mode because we don't have numerical data, but we have only labeled data, water and non-water level. And another parameter is the search radius, so the number of non-empty neighbors in which we are evaluating the statistical mode. And we perform the gap interpolation in 2 consecutive steps. The first one is for both classes with a search radius very small of 2 cells in order to fill small gaps due to maybe occlusions or reflective surfaces or areas very close to the raster edges. And the second interpolation was performed only on water level pixels with customized search radius according to the size, and then I will explain why. And the idea here is to fill the majority of gaps over water in order to obtain this one. So an interpolated binary scene clustering, but with all the gaps filled on water. At the end, the final step, here we have the binary scene clustering with interpolated water surfaces and original DSM with gaps. And the main question is, does the empty pixel in the original DSM correspond to water pixel in the binary scene clustering. If no, for example, that red dots there, which is gaps due to canopy tree occlusion, we left the gaps. If yes, for example, here where we have the natural acquisition on water, we can substitute the gaps in the digital surface model with the mean water level elevation. And at the end, we are able to obtain the final digital surface model completed over water, and with an additional inverse instance weighting interpolation, we are also able to fill the gaps classified as non-water. So I would like to show you some results. This is the RGB imagery in two different sites, lakes, and then we have in the second column the water-filled digital surface model, which is the product of AQUA-LIDAR, and on the right the digital surface model obtained with cloud compare that used the simple linear interpolation, so without passing through the classification. As you can see here, overall, both methods perform very well when we don't have gaps. So on target classes that are not water, but when we are in the riparian zone, very close to the emergent vegetation, such as, for example, in Lake Pusiano, we have water, and then we have some riparian vegetation. As you can see from the imagery, the digital surface model obtained by cloud compare performs worse because it used the elevation information provided by the vegetation to fill the gaps over water, and also there, this is the tree canopy in Lake Massachusetts. This is the tree canopy, and they use the elevation to fill the gaps. And what happens is the bias in elevation in the final digital surface model of about 5 to 10 meters in some cases, and this is the same example in Lake Massachusetts, but within a different area of the study site where there are some man-made structure for fishery, and this is the difference between the two products, as well as in Lake Garda, where we have mainly man-made environment, and the digital surface model with cloud compare use the information of elevation of boats to fill the gaps over water. And the last things I want to show you is about the completeness of our products, because the completeness is very simple. It's defined as the ratio between the number of non-empty pixels with respect to the total pixel in the scenes, and we evaluated the completeness at the end of the most significant steps of the workflow. And as you can see from this graph, we have on the x-axis the different sites, and on the y-axis the scene completeness at the end of specific steps. As you can see, at the end of step 2, we have variable scene completeness, and is site specific. It depends on the amount of data gaps we need to fill, and it depends, for example, on the water land proportion within the surface areas, on the flight direction, and on the number of occlusions. Here, for example, you are able to see the scene completeness when it's high. For example, in Lake Pusiano, you have a low number of gaps that need to be filled. On the contrary, in Lake Garda, site 3, you have, for example, vegetation with low density, canopy gaps, and the scene completeness is lower. But as you can see from the bar plot, at the end of step 3, when the gap interpolation process is finished, you obtain more or less 97–98% of scene completeness. Even the scene completeness at the end of step 2 is different. This is a sort of hint about the transferability of the model and the fact that it's able to fill the majority of gaps over water. But at the end, we are able to reach almost 100% of completeness. It's not completely 100% because we have some remaining gaps, less than 1%, in water level Plus, if our gaps on water are very high, are huge, or in non-water level, if we have some occlusion gaps due to, I don't know, canopies, tree canopies that are very high, so the algorithm is not able to fill completely the gaps. But I think that at this point is we have to understand if our objective is to have a complete DSM or an accurate DSM. Because if we have a complete DSM, you can iterate the gap filling process until you can reach the 100% incompleteness. But if we want an accurate DSM, you have to stop there and to see, okay, I'm not able to fill completely my DSM, but I know that the elevation that I estimate are more or less reliable and accurate for my purposes. To jump to the conclusion, this is my method, so it's an open source software. At the moment it's very ugly, it's like this on my computer, but I plan to publish it on GitHub as soon as possible, and the idea is to provide a very simple method that could be transferable to other sites. But there are some challenges because, for example, we tested this method only on floating and emergent macrophytes that are able to reach 3 to 4 meters above the water level, but we have a lot of floating macrophytes with different elevations with respect to the water surfaces of about 50 centimeters or 10 centimeters. That could be challenges, as well as try to understand if we are able to move from local to regional scales by, for example, transfer our method to other LiDAR platforms, such as, for example, the airborne ones. And as well, the method has some limitations. For example, in the second step, we have that we move from 10 cluster to the binary sync clustering with an expert in evaluation and identification. And other possibilities for the futures are, for example, using multispectral LiDAR data, but this is a very expensive solution, or to add more features in order to detect automatically what is water level and what is non-water level. And the last thing is the limitation due to the gap interpolation tuning, because as if you remember, we interpolated our data with the search radius that was depending on the sites, and the reason is this one, because our analysis revealed that there's a sort of negative linear trend that correlates scene completeness at the end of step 2 with search radius. And as you can see, for example, here, if we have a site with a high scene completeness, that means that you have a low number of gaps that need to be filled. The search radius is low. While if you have a site with a scene completeness that is low, this means you have more gaps that need to be filled, the search radius is high. So I'm not able to provide you the exact value of search radius in order to use it in the model, in the algorithm, but I am able to tell you what about the possible range in which you can parameterize your search radius. This is all, and thank you for the attention.